Today we will talk about conservation theorem for linear momentum and angular momentum of a system of particles. Let us consider first a system of particles. There is a space coordinate and we have large number of particles because we are considering a system of particle. And let us consider this is our first particle having mass m1, position vector r1, and it is moving with velocity v1. Similarly, let us consider this is our second particle with respective position vector r2, velocity m2, and mass m2. And similarly, this is our ith particle, and the position vector of ith particle is ri, the mass is mi, and the velocity of the ith particle is vi. And this is our nth particle, which is represented with mass mn, velocity vn, and the position vector rn. And these are our three axes, x-axis, y-axis, and z-axis. Very well know that the position vector are given in the terms of x coordinate, y coordinate, and z coordinate. If we are discussing about first particle, we can give the corresponding coordinate as x1, y1, z1. Similarly, we can represent r2 vector, position vector r2, position vector ri, and so on, the position vector rn. First, we will discuss about the linear momentum, conservation theorem for linear momentum for many particle system. If we have a single particle, then we can give the external force applied on the particle is equal to the rate of change of the momentum of that particle with respect to time period. But now we have large number of particles here. Let us consider this is the external force which we are talking about on the ith particle. Then the external force on the ith particle will make a change in the position vector of the ith particle. But we have to discuss about all the particles. It means we have to take the external force of first particle as well as the external force of the second particle, and so on. We have to take the total external force on each and every particle. Let us consider the total external force is given like this. It means the sum of all these external forces can be represented as summation of the external force on the ith particle, and we can give the limits to the summation from I is equal to 1 to n. Similarly, what pi is representing? Pi is representing the momentum on the ith particle. But now we are discussing about the system. If pi is the momentum of the ith particle, then summation of the pi will give the momentum of the first particle, the momentum of the second particle, and so on. We will obtain the sum of the all the momentums of each and every particle. Now, this is the equation we have written for the ith particle. If we take summation on both the side, it means now we are talking about the system. If we are talking about the system, just change all the things in from single particle to many particle, then we will get this summation can be represented the total external force. It means we can write this summation as Fe, where E represents the total external force, is equal to, here summation of dpi upon dt is representing the change of the momentum of the ith particle. But if we are taking the summation, it means representing the summation of all the particles. In our last lecture of center of mass, we very well know that the momentum for the whole particles, if p is representing the momentum for all the particles, that is equal to p, that is p is equal to summation of pi. P is the total momentum of the system. We can give this in the terms of center of mass also. This can be represented as d upon dt, capital M and capital V. and in subscript we can write Cm, where Cm is representing the center of mass. It means the total momentum of the whole system can be represented as the momentum of center of mass, where m is representing the total mass of the system and vcm is representing the velocity of center of mass. It means the many particle system can be converted into single particle system by taking consideration the whole system is converted into single mass particle, where the position vector of the single particle is the position of center of mass and the velocity of that single particle, it is the velocity of center of mass, and the mass of the single particle that we have assumed is the total mass of our system. Then P is representing the momentum of center of mass. Here, from this conclusion, if we put a condition external force is equal to 0, if external force is equal to 0, it means the right hand side expression is also becomes equal to 0, and it only happens when the term dp, that is change in the momentum, is equal to 0. If the change in the momentum is 0, it means the physical quantity is not changing with time. It means the physical quantity is constant, or physical quantity is a conserved quantity. It means it is not varying with time. This is the law of conservation of linear momentum for many particle system. If the total external force on whole system is equal to 0, only at that condition the total momentum of the system also remains constant. Now if we talk about the center of mass, what happens the momentum of the center of mass, this capital P is representing the total momentum of the system. It also corresponds to the momentum of the center of mass. It means when the external force applied on a system of particle is equal to 0, the momentum of the center of mass is constant, or the total momentum of the body is also constant. If momentum is constant here, then according to this relation, what will happen? If P is constant, mass is constant on the right hand side, it means vcm is also constant. Hence we drive a relation that is the inertia constant, what it is representing according to the law of inertia. If external force on the body remains is equal to 0, if the body is moving with a constant velocity, it will move with a constant velocity. Then from the second equation of motion, we proved the law of inertia also, that if the external force on the body is equal to 0, the velocity of the body also remains constant. This is our law of conservation of linear momentum for many particle system. Now secondly, we have to prove the conservation theorem for angular momentum. Now we will first drive the relation in between torque and angular momentum, and then we will put the condition on the torque, and then drive or find out what happens to the angular momentum when the external torque is taken as 0. Again, we are considering the same system as we have considered in this very derivation, that we have taken n number of particles having masses m1, m2 and up to mn, velocities v1, v2 up to vn, and the position vectors are represented by r1, r2 and rn, which are given with the help of the coordinates along x-axis, y-axis and z-axis. In the same way, we can represent r2, we can represent up to the position vector rn. Here now we are moving toward our second derivation, that is law of conservation of angular momentum. Again, we are taking our ith particle. If Ri is the position vector of the ith particle and Pi is the linear momentum of the ith particle, then the relation Ri cross Pi gives the angular momentum of the ith particle. This is the relation between angular momentum and linear momentum for the given particle. we are not discussing about a single angular momentum. We have to discuss about the total angular momentum of the system. If we want the total angular momentum of the system, we will have a summation on the each and every particle's angular momentum, and we will have Li is equal to summation Ri cross Pi, and this is giving the total angular momentum of our given system, which we can represent with the help of capital L. We very well know that angular momentum is a vector quantity whose magnitude is given by r cross pi magnitude. You can calculate by the cross product of these two given vectors, and with the help of right hand thumb rule we can find out the direction of L also. Now from the relation between the force and the momentum from our second law of motion, from Newton's second law of motion, we know that dpi, if we are talking about the ith particle, the rate of change of momentum of the ith particle can be given as the total force on the ith particle, and the total force on the ith particle is given as the external force on the ith particle and the forces on the ith particle due to the other particles, which can be represented with the help of the factor fji summation, where fji summation is representing the part all the particles giving a mutual force to the ith particle. If we expand this summation, we will get f1i, f2i, f3i, f4i, but we are taking here a condition I is not equal to j. It means we are representing all the total internal forces by all the particles on the ith particle. Now, if we cross product this very equation with Ri, then what will we get? We will have Ri cross dpi upon dt is equal to Ri cross Fie, that is the external force representation, plus Ri cross, that is Fji, and now we are just expanding this expression for whole system. It means we have to represent summation on each and every term. Here we it is representing the internal force, which we have already represented with the help of a summation here. Already we have a summation here, and we are summing up the terms from j is equal to 1 to n, and now again we are just cross product this equation with respect to Ri and putting the summation for to get the result for whole system. Now already we have a summation, we are again putting a summation with respect to I. It means this particular term is having sum up with respect to I as well with respect to j. Here is the condition: I and j varies from 1 to n, but I is not equal to j. This single summation is not representing single summation, it is representing two summation. One is expanding with respect to I 1 to n, and another is representing summation j is equal to 1 to n. We instead of two summation, we are just using a single summation, but we are putting the all the conditions of the two summations here. Now if we expand this expression, what we will get from our expression we will find out. And here we left from this expression L is equal to Ri cross Pi, and if we differentiate this, what will we have? That L is equal to Ri cross Pi, this is for the ith particle, but if we put a summation, we will get the total angular momentum here. We are just differentiating the equation with respect to time here. What we will get, we will have dl upon dt is representing the change of total angular momentum for many particle system with respect to time period, and here we are differentiating this term with respect to time. We will get d upon dt summation of Ri cross Pi. We have to differentiate this term. Now, just taking the right hand side, we are just taking Ri as constant and differentiating Pi with respect to time period. And now we are differentiating Ri with respect to time period and taking Pi as a constant according to the rule. If there are two vectors in product and we have to differentiate them, we have to take first factor or first vector as constant, differentiating the another, and adding another term in which we differentiate the first factor and taking the another factor as constant. Now, just expanding this relation, what will we help? Ri cross dpi upon dt. The first term we have taken as it is, plus now the second term, that is dri upon dt plus pi, that can be written as change of position vector with respect to time period, that is representing the velocity of the ith particle, and this pi can be written in the terms of the momentum of the ith particle, that is mi vi. Here there is a cross in between these two factors. If these two terms are in cross product, it means both are vector quantities, but here mi is not a vector quantity, it is scalar quantity. It means we have taken vi cross vi, and we know that if similar vector undergo cross product, we will get 0 because angle in between them is equal to 0. It means this term becomes 0, and we will get dl upon dt is equal to only this term, and this term is our ri cross dpi upon dt, and let us consider this is our equation number 1. Now we have another factor also, which we derived from the external and internal forces. This is our another factor, and this factor is ri cross dpi upon dt, and now this vector is also our ri cross dpi upon dt. It means this whole term is representing the change of angular momentum with respect to time period. If we put this equation number 2, then using equation number 1 and equation number 2, we will find out that dl upon dt can be written in the terms of the internal and external force, that is ri cross fi external force plus summation ri cross fji, which is representing the internal force, where ij are moving from 1 to n, but the condition is that I is not equal to j. Now we will solve this term. This term is representing the cross product of our position vector of ith particle with respect to our internal forces. We will find out what this whole cross product will give us. This value ri cross fgi, what it is representing, it is representing the jth particle is applying the force on the ith particle, and if we are summing both these variations j and I, we can obtain all the type of forces, and here all the radial vectors. It means we can just change this expression by taking any another particle j here. If this is our j particle and the position vector of the jth particle is rj, the velocity of the jth particle is vj, and the mass of the particle is mj, then we can represent the whole equation. Instead of I, we can represent this whole term in the terms of j. Then if we write this rj cross fij, that these two terms representing the same factors or same terms, just to put all the values of I and j here from 1 to n. Condition is that I is not equal to j, and here also if we put I from 1 to n and condition is I is not equal to j, if we just expand these two summations, we are getting the same results. We are getting all the internal forces here as like we will get from the this factor. It means these two terms are equal terms if we get summation along all the particles. Now if we add these two terms, it means we are just taking double of these two vectors. It means if we are taking Ri cross Fji plus Rj cross Fij, we are just doubling our terms. We are just doubling this factor. But we have to take single time this factor. We will take half of this term. We by using this type of changes, we will find out what is the relation in between the position vector and the mutual forces in between the particles to each other. Now we can put half as half, summation as a summation. What is the relation between Fgi and Fij? First ith particle is applying force on jth particle. Similarly, the jth particle is applying the force on ith particle, but the situation is that they are similar in magnitude but opposite in direction. It means we can put Fji is equal to Fij in magnitude but opposite in direction. Now we are just substituting Fij term in the terms of Fji, then we have to put the negative nature of the force. Ri cross Fji, we are just substituting this term as it is, but here we are taking minus because we are putting Fij here Fgi, then we will get Rj and cross with Fji. From this expression, what we are getting, we are taking Fgi and Fgi as common. If we are taking Fgi common, we have Ri position vector minus Rj position vector. Now we will expand this Ri and Rj position vector, what they are indicating to us in this expression. Let us consider the whole system, but now we are only considering the ith and the jth particle, and here Ri is representing the position vector of the ith particle and Rj is representing the position vector of the jth particle. According to the triangle law of vector addition, if we take a vector along this direction, it means these two vectors, that is Rj and this vector, they are in representing their self in anticlockwise direction. Then this very vector will give the resultant of these two vectors. If I represent this vector in the form of Rij and this is in this direction, then what is the relation in between all these vectors according to the triangle of vector addition? If two vectors are in the same direction, then the closing side of the triangle in the opposite direction will give their resultant. It means Ri is equal to Rj plus Rij, and what happens to Rij? Rij can be given as Ri minus Rj. Then from our last expression, that is this, where we have taken Fgi fji common, we get ri minus rj. This ri minus rj can be represented by the displacement vector of these two position vectors ri and rj. We can change the expression in the form of rij. Then what will we have? We will have, that is, half of summation rij cross with fgi, which we already taken constant from our last expression, and we are just expanding our this expression in the terms of our mutual forces. This vector is representing the displacement vector in between j and I. This vector is representing the force of the jth particle on the ith particle. Every book have their different notations. Sometimes in one book is representing the fj is representing the force of on ith particle due to jth particle, but in some books this notation is representing the force on the jth particle due to the ith particle. Just take it, consider it in your words what you are just considering fgi, whether you are taking as it is the force on the ith particle due to jth particle or the force on jth particle due to the ith particle. Now, what is the relation in between the direction of these two vectors? If we are representing, these are our ith and jth particle, and this is the direction of our displacement vector which we are representing rij, that is we are moving from j to the ith particle. And if fji here is representing the force on the ith particle due to the jth particle, then what is the direction of fji? If these two particles are neutral particles, they are not charged particles, they have mass mi and mg, they have a gravitational force in between them, and jth particle will apply a force on the ith particle. If jth particle is applying a gravitational force on the ith particle, it means the jth particle is attracting the ith particle in its direction or towards its center. This will be the direction of fgi, and this is the direction of rij. Then the angle in between them is 180 degree. If two vectors, if we open this cross product, we will have the magnitude of rij, magnitude of fgi, and the sign of the angle, smallest angle in between r and f, and here the angle in between them is 180 degree, hence the sign 180 degree becomes 0, and in this case the whole resultant term will be 0. If we take the force Fij, then it means we are taking the force on jth particle due to the ith particle. Here the ith particle will attract the jth particle in this direction, and now the force is Fij. Here rij and fij are, they are in the same direction. It means the angle in between them is here 0. Again sign 0 is 0. It means in each and every case, whether the particles are attracting or they are repelling, this whole term, in the case of internal forces or in the case of mutual forces or in the case of many particle system, the particles will have a relation like that. The displacement vector and the force always their cross product will be 0, whether they are in same direction, whether they are parallel or whether they are anti-parallel. It means these two vectors are always co-linear to each other, maybe parallel, maybe anti-parallel to each other. These two vectors, that is the displacement vector of I and j and the force in between the I and j, these two vectors are collinear vectors. It means they may be parallel to each other or they may be anti-parallel to each other. In each and every case, this whole cross product is always equal to 0. It means this term is going to be 0. If this term is 0, what will happen to our equation? We find out this whole term becomes 0 in our expression which we already derived, we will get dl upon dt is equal to summation of ri cross fie. And what is the cross product of angular radial vector and the external force Ri cross Fi, external force on the ith particle? It represents the torque on the ith particle. If this is the external force, it means we are representing the external torque. If we are giving summation operation to this factor, it means we are summing up the torque also, and on summing all the torques we are getting the total external torque. By using this expression in our equation, we will get this whole term is nothing, it is the total external torque. Then what will the relation in between torque and angular momentum? Then the external torque, that is represented by 2e, is equal to the rate of change of total angular momentum with respect to time period. Now we proved the relation in between torque and angular momentum. We will move towards the law of conservation of angular momentum. If we substitute a condition that the total external torque is equal to 0, then what happens to the angular momentum? Change of angular momentum with respect to time is equal to 0. It means time के साथ आपका angular momentum change नहीं हो रहा है. अगर time के साथ angular momentum change नहीं हो रहा है, it means our angular momentum here is a constant quantity or a conserved quantity. Hence the angular momentum is constant or conserved only when the external torque on the body or on the system which is in angular motion, if it is experience no external torque, it means it will move with a constant angular velocity or it is moving with a constant angular momentum. This is the whole expression, or this is the whole talk about the relation in between torque and angular momentum. And what is the condition? Angular momentum remains constant. Angular momentum will remain constant only when the external torque applied on the system is equal to 0.